So we talked about permutations, which is a way of counting discrete objects when the order in which the objects appear matters. But what if the order doesn't matter? There has to be some other way of counting them. When selecting them, it doesn't matter the order in which I select them, and those are called combinations. We still have the same two categories, if elements can repeat and if elements cannot repeat. So let's begin the conversation about when elements cannot repeat. The formula for this is going to be the same formula that we saw for permutations, where we take n factorial over n minus r factorial, but because the order doesn't matter, there's a very good chance that we could get duplicate combinations. For instance, 1, 2, 3, and 3, 2, 1. As a permutation, each one of those would be distinct objects. But in a combination, they're actually the same because the order in which they're taken doesn't matter. Which means that I have to add r factorial to the denominator of this equation in order to remove the duplicate sets like this. So going back to my analogy that you've built a bunch of homes and you've taken your 6 brand new homeowners down to the pet store and you're going to allow them to choose puppies. What happens if the order in which they choose the puppies doesn't matter? It doesn't matter if the first home buyer goes first or the second home buyer goes first. The only point is you send the 6 of them down there and they're going to choose their puppies. We're going to find out under this circumstance the order in which they choose doesn't matter, but we're going to find out that we can still not have repeating elements, because once a homeowner chooses a puppy, that puppy is gone and cannot be chosen by the next one. So let's write down the scenario. We have 15 puppies and we are going to choose 6 of those puppies. I cannot have repeating elements because once a puppy is chosen, he is no longer available. And so this is going to be 15 factorial over 15 minus 6 factorial, but I also have to take into consideration all of those duplicate values, and so I'll put 6 in the denominator as well, 6 factorial. So this is going to give me 15 factorial over 6 factorial, 9 factorial. So if I were to simplify this, if I break it out into its factorial, I can remove the 9s, and I'm going to go about trying to remove or simplify it even farther. So I can see that 5 and 15 goes into 3 times 5, so we can factor out that 5. I can also factor out that 3. I can see that 14 is actually equal to 2 times 7, so I could remove those 2. I can see that 12 is actually equal to 3 times 4, so I could remove the 4. I can see that the 6 is actually 2 times 3, so I could remove that 3 and this 3. And what we are left with is 13 times 11 times 10 over 2 times 1. And ultimately this answer is 1100 divided by 2, which is going to be 550. So there are 550 ways that my 6 homeowners can choose a puppy out of the 15 at the puppy pound. All right, so now you just found out that not all of your homeowners like dogs. So at the puppy store, there are 15 pups, there are 12 cats, and there are, let's say, for instance, 30 fish. What happens if you wanted to allow your homeowners, 2 of them to choose pups? What if you wanted to allow 1 of them to choose cats? And what if you wanted to allow 3 of them to choose fish? How are we going to go about doing this? Well, I know that we're going to allow some to choose pups, some to choose cats, and some to choose fish. So I'm going to use my sum rule because they can choose pups or cats or fish. And when I use the or operator, it implies a plus. So how many different ways are there that they can choose pups? Well, there are 15 pups, and we said that 2 of them can choose pups. If there are 12 cats, and we said that 1 couple or 1 family could choose cats, and there are 30 fish, and we said that there are 3 people or 3 homeowners that can choose fish. Let's see if we can figure out what this answer is. So let's figure out the cats. 15 choose 2. I'm going to have 15 factorial over 2 factorial times 15 minus 2 factorial. That's going to give me 15 factorial over 2 factorial times 13 factorial. I should be able to cancel out those 13 factorials. 2 factorial is actually 2 times 1, so if this is 2 times 7, I should be able to take out the 2. And ultimately we have 15 times 7. So this gives me 105. Let me move this down a little bit and see if we can figure out our cats and our fish. So for our cats, we have 12 cats, and they're going to choose one of them. This is going to be 12 factorial over 1 factorial, 12 minus 1 factorial. I can simplify this by removing the 11 factorials, and this is going to give me 12. It would make sense that if I'm only going to choose one of the cats, and there are 12 of them, that there are 12 ways that I can do that. And finally, the last one is the fish. I'm going to choose 3 of the families will choose fish. That becomes 30 factorial over 3 factorial, 30 minus 3, which is going to give me 27 factorial. If I simplify that down, those 27 factorials go away. This is actually 3 times 2. I'm pretty sure that this is 2 times 15, which means that I could take out the 2's. I'm sure that 15 is actually 3 times 5, which means that I could take out the 3. So ultimately I have 5 times 29 times 28, which is equivalent to 4,060. So there are 157 different ways that they can choose the pups. There are 12 different ways that they can choose the cats, and there are 4,060 ways that they can choose the fish. I'm going to use the sum rule to add them all up, and we're going to get 4229. So this is the formula that we use when the order in which the items are selected does not matter, and the items that I am selecting are removed from the population when they're chosen. For instance, the pups or the cats or the fish. When we choose them, they are no longer available for the other families to choose. But what if selecting an item out of the population does not remove it from the population? What if I can have repeating values?